It is important to remember that our data analysis is trying to determine the relationship between our variables and not necessarily what the graph is doing. We use the graph to show the relationship, but our concern is not about x and y as it is about our variables, in this case d measured in meters and t measured in seconds. We can use any variables with any units, but we're concerned with the relationship between these variables and not just what the graph is showing us. So when I look at a graph like this with a curve going up and I use my yellow sheet shows me that I have this shape. It tells me that y is proportional to the square of x. I know that I'm going to want to graph whatever my y variable is, which in this case is d, versus my x variable squared, which is time. So I'm going to need to produce a d versus t squared graph. So I would state that the relationship is that d is proportional to t squared. Using d and t is preferred because y and x are not used on this graph. In looking at this relationship, if this is the relationship, it means that we're going to end up with an equation that might look something like this. Position is equal to some coefficient multiplied by time squared. This coefficient could be anything, but we know that's going to be the relationship. If we do a very simple example of d equals t squared, and I fill in my data table, 1 squared will be 1, 2 squared will be 4, 3 squared 6, 4 squared will be 16. So when I ask about the meaning of this relationship, what I want to know is if I make a change to my independent variable, what change will I see with my dependent variable? So I would like to know if I do some change to time, for example, if I were to take time and double it, what is going to happen to my dependent variable, which in this case is my d value? Well, looking at my data table, I can see that if I go from 1 to 2, that's doubling, and I'm going from 1 to 4. That's going to be an increase of 2 squared. I've got the squared there. That's why it's going to be times 4 when I look at that relationship. I can look at the same thing here. If I go from T2 to T4, that's also doubled. 4 times 4 gives me 16, so this relationship stays. So I always state the independent variable first and what change I make and what change will result with my dependent variable. So that shows me my relationship, and now that shows me the meaning of my relationship. What does it mean in terms of the actual values? So my new graph, as suggested by the gold sheet that we have, tells us to graph d versus t squared this time. Having a title is a good habit to get into. And now if this is truly the relationship, which is what we think it is, we would get a straight line. It could be that this curve up here is part of a much more complicated equation and that this doesn't happen and we would have to continue on with something else. In this case, we're going to say it does in fact produce a straight line. So I know that the column I had to make was whatever my relationship was. This unit is still measured in meters. Whatever I do to my variable, I must do the same thing to the unit. So if time is measured in seconds, then time squared will be measured in seconds squared. Now, if I'm lucky enough to get a straight line, I know that a straight line is y equals mx plus b. This is my mathematical equation. What I'm going to do is replace it with the variables in my graph. Y is position d. Slope is going to be a value calculated by our computer for us. X is time squared in this graph, so I'm going to have some value here for my slope m, my x variable and y equals mx plus b. That x variable is going to be t squared. And then if I have a y-intercept, I will include it. In this case, I'm going to say that it's 0. It looks like it's 0, so we'll call it 0 for this one. This equation, let's say that the slope value is given to us. Let's use an easy number like 2. I plug in 2. Every number in my equation must have a unit. So to determine what the unit is going to be, I show my work of how I would calculate slope, rise over run. I do not need to use numbers because I will have found the slope using the computer. So all I need to do is replace the letter y with the unit for y. I come over here. This is my y variable. It's measured in meters. So I write in an m divided by whatever my x variable is, in this case, seconds squared, and that's my unit. If I have a second division bar, I need to use some algebra, multiply by the reciprocal, so that I have only one division bar. So this equation is not complete until my number 2 here has a unit, meters per second squared. And even this 0 over here needs to have a unit. Since it's the y-intercept, that means it's a y value. Y is measured in meters. So what I have just done is I have taken my curved graph, found the relationship, determined that that relationship shows that whatever I do to my time variable, I do the same thing squared to my d variable. I have figured out what the slope unit's going to be by using my slope equation. I've made my new graph, graphing whatever this happens to be here. So I have a t squared measured in seconds squared. And if it's truly this relationship, it produces a straight line. And now I simply replace all of my letters here with either physics letters or numbers generated by my computer. So my final equation in this particular instance would be d equals 2 meters per second squared. I prefer putting the number and unit together in parentheses, so I know that is one value, times time squared plus 0 meters. And so I've done all of that by using my gold sheet. There's my shape, there's my relationship. It tells me what I should graph, and it even tells me at the end what I would expect to see. I would expect to see my y variable, my x variable squared, the slope, and a y-intercept, and that is exactly what we have here. Y, x squared, our slope with the unit, our y-intercept with the unit. That right there is for a squared relationship between our two variables.